Okay. After we've done this, I will sketch a proof of the index theorem, and well, this will be a sketch, not really a detailed proof, and this will be it. Now, does anyone know when the semester officially ends? Oh, really? Well, nor do I. Anyway, I think we'll probably okay. Well, today's the 10th. Tuesday's the 13th. So we definitely have next week. We may or may not have another Tuesday the week after. Well, we'll find out.
Ну, согласно графику учебного процесса, сессия начинается 21 декабря.
Well, then we're in luck. The 20th is an official semester day. So, well, yeah. So let's do as many examples as we can, and then on Tuesday next week, I'll sketch a proof of the theorem. Anyway, let's see. Okay, does everyone have problem sheet 4? It's in the same directory as everything else, basically. Okay, so there's one particular thing we want to cover in some detail, but well, most of the problem sheet is relatively straightforward. Okay. Well, let's have a look at question 6, I think. The first part of this question is something we did talk about last time. No, not the first part. The paragraph before question 6. Let's have a look at this paragraph and see if it makes sense. Well, there are some typos, by the way, which we'll correct as we go. Blah 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 blah. M is even. Well, so far so good. L 1/2 M. Okay. Using question 12 from the previous problem sheet. Well, let's assume question 12 from the previous one. we can use the splitting principle for orientable real bundles, which means we only have an injective map in rational cohomology, not necessarily in integral cohomology, but never mind. And the bundle, the pullback splits as a direct sum of two-dimensional or rank 2 oriented real vector bundles, and if the rank is odd, there is one more one-dimensional summand, which is not there because we assume the rank is even. Blah 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 blah. By complexifying everything and using question 5, we see that. Okay. Let's assume this works. What it says is if I take a real vector bundle of rank 2 oriented, and I take the complexification, the result splits as L plus L conjugate, where L is some line bundle and the conjugate is the conjugate bundle. Basically, this it's a theorem we already saw at some point early on, but in disguise. Namely, every oriented rank 2 real vector bundle has a natural complex structure. Basically, since the bundle is oriented, I have a metric. Well, I always have a metric, but since the bundle is oriented, I can take a metric, and I can take a rotation through pi over 2 with respect to this metric. And when I say through pi over 2, I use the fact that the bundle is oriented. Otherwise, I wouldn't be able to tell apart pi over 2 and minus pi over 2. Okay, does this make any sense? If it doesn't, just let me know. Okay. Anyway, I have this decomposition which is written before question 6. Does everyone see it, and does it make sense? Leonid, does this decomposition make any sense?
I'm trying to find this decomposition.
Have you found problem sheet 4 on the characteristic classes?
Yes, I just opened. Okay, I see. Let me think. Is it a consequence of the splitting principle that we just discussed now?
Well, it's the splitting principle, but for real oriented vector bundles.
Yes.
In more detail, we introduce a complex structure on every EI, which makes it a complex line bundle, and then use the fact we already discussed several times. If I take something which is already complex and complexify it again, I get this something plus the dual of something.
Okay, and here we need to use some metric.
Yes, here we need to use some metric. Well, for example, we could take the Euclidean metric we use to define the complex structure and complexify it, get the Hermitian metric.
Okay, now it is clear.
Okay, Volodya, is it clear?
Yes.
Saman,
Yes, it is.
Philip,
Yes.
have you found problem sheet 4?
In the drive.
Yes, it's somewhere in the Google directory.
Yes, I haven't.
Okay, now go to question 6. The formula on top of question 6 doesn't make any sense whatsoever. Oh, by the way, there is a small typo in the formula. Let's correct it. Uh, uh, okay, Philip, have you does this formula make perfect sense, no sense whatsoever, or something in between?
Something in between. I'm trying to it's like is it splitting principle or something similar to that?
Well, yes, it's the splitting principle, but for real oriented vector bundles, which means we want not just a direct sum of bundles, but we want a direct sum of oriented bundles, which means they will come in the individual pieces will be will not no longer be line bundles. They will be real oriented of rank 2. And well, the idea is the same. We take the Grossmannen of oriented 2 planes and use it to split off 1 2-dimensional sum, and then we repeat the procedure until there's until the remainder is either 0 or has rank 1. If it has rank 1, it's oriented on rank 1, so it's trivial. If it's 0, well, we're done. So the decomposition we have is a sum of oriented bundles of rank 2, plus maybe a one-dimensional a rank 1 trivial remainder if the rank is odd, which is not the case. Let's forget about it. So we take this decomposition and then we complexify it, and then we get a sum of complex bundles, complex line bundles, plus plus the sum of the conjugates, which is the same of the duals. One can identify the conjugate with the dual using a Hermitian metric. Okay, now Philip, let's look at the formula again. Do you have any questions on?
What do you mean by lambda odd and lambda even?
Well, we're coming to that. So lambda even is the sum of the even lambdas, and lambda odd is the sum of the odd lambdas. What does this mean? Well, this means we take the exterior algebra on some vector space, and then inside this exterior algebra we have the even and odd components, and we group them in. We put the even ones in lambda even and the odd ones in lambda odd.
And what is minus?
Well, actually, it's a good question, and more generally, what's inside the CH? So we have CH of something, and what is this something? Where does it live? Well, it lives in the K of X. Inside K of X, we have this. We can add and subtract, and even multiply, tensor multiply vector bundles. Okay, I'll write this down. So everything that happens in question 6 happens inside the K. Inside the K, inside the ring K of X, where we can add and multiply vector bundles. Okay, now the formula. Where does the formula come from? Well, in K of X, we have well, first of all, okay, let's start with a plus. No, sorry. Let me. Let me do it like this. So suppose we have some number of line bundles. Okay. So first of all, let's remark the following thing. I have the following identity in K of X. In other words, inside the ring of vector bundles, complex vector bundles on X. Does this identity make any sense?
What is one?
One is the unit of K of X as a ring, and well, this one is also represented by the trivial rank 1 vector bundle.
Yeah, okay.
Leonid, does this formula make any sense?
Yes, it's clear.
Okay. Now, well, in this formula, I have pluses, but instead of pluses, I could put minuses, and the formula will still make sense in the K ring, and the result will be lambda even minus lambda odd. Philip, does this make any sense whatsoever?
Yeah.
Oh, by the way, what is E? Before E was a sum of L1 plus L2 plus Lm plus L1 dual plus L2 dual plus so on.
Yes. So the formula which I've just written is valid for an arbitrary collection of line bundles.
Okay.
Now let's specialize to the case when E is L1 plus L1 dual plus etc. plus LL plus LL dual. And we then use the fact that CH CH is a ring homomorphism. In particular, CH ring homomorphism from K of X to the completed rational cohomology of X. Okay, now, well, it's a ring homomorphism, so I use this fact, and then what is CH CH of Li? Well, it's e to the xi. That's basically the way we define the Chern character. Okay, well, for exactly the same reason, we have CH CH of Li dual is e to the minus xi. Okay. And then I basically use the fact that CH is a ring homomorphism, and I get this mysterious formula, which is no longer mysterious. Okay, Saman, does the formula make sense now? The formula for
The second part, why is for dual we have e to the minus xi? I mean, is that part of definition or no? It's
well,
we can prove this.
the first Chern class of the dual is minus the first Chern class of.
Yes, I see. Thank you.
Okay. Okay, so basically we use the fact that CH is a homomorphism and the definition of CH. Okay, now does anyone have any questions on part A of question 6?
Well, I have a question about what is meant by this complete cohomology.
Well, this means we have we just take the direct product of all cohomology groups with Q coefficients. Not the direct sum, but the direct product.
Yeah, I see.
And well, we need it because if X is infinite dimensional, then the definition of CH still makes sense, but the exponential will be an infinite series. Are there any more
How
questions?
did we get that? How did we get that formula for exterior power of E?
The first one.
Yes, this.
Well, basically by inspection. the exterior power of okay, let's expand the left hand side. Well, first of all, by inspection, we'll have well, this formula, and then lambda even is the part which corresponds to I, capital I, having an even number of elements and the same for lambda odd. Значит, нет, понятно ли, что происходит?
Ну, разложение понятно. Не очень понятно, как это с внешней степенью связано.
Значит, как это связано с внешней степенью? Ну, давайте посмотрим, а что такое, значит, что такое внешняя степень от что такое внешняя степень от прямой суммы значит, одномерных векторных расслоений. Какая это внешняя степень? Well, let's write it down. Lambda I of L1 plus etc. plus Lm. Same claim as the result is the sum for I equal M, the product where I again is a subset of 1 etc. M. Does this formula make sense?
Is this product a tensor product?
Yes.
Okay, I think now everything is clear.
Okay.
Thank you.
You're welcome. Are there any more questions? Okay. Now the first formula is clear. Now what about the second one? Well, the second one basically says that the is basically a consequence of the fact that the Euler class is the top Chern class. What was the question?
Oh no, I was just about to say the same thing.
Okay, so we know the first Chern class of Li, that's Xi by definition. Okay, now we know that Li is isomorphic to Ei as an oriented rank 2 real bundle. So the Euler class of Ei is again Xi. And I know that Q upper star of gamma gamma tilde decomposes as a sum of EIs. So we get the product of Xi's. Okay. Well, we have less than 1 minute left. Are there any questions on part B? Well, I think part B is straightforward. Okay, if there aren't any questions, let's reconnect again and then move on to question 7. I think yes, question 7.